In this question, we're going to maximize the area of a trapezoid given certain conditions. We have the trapezoid shown, and we have a side length of 2 and another side length of 2 and a side length of 3 along the bottom. We don't have to worry about the top, how long that side length is. It'll be plenty long. So we won't have to worry about that. And what we want to do now is figure out the area of that inner trapezoid. So what we're going to do, we're going to think of that inner trapezoid as consisting of a triangle as well as an identical triangle on the other side. So it's going to be, the area of that trapezoid is going to be 2 of those triangles, and then it's going to be one rectangle in the middle, that rectangle in the middle, plus the area of a rectangle. Now, what is the area of a triangle? Well, we know the area of a triangle is 1/2 base times height. And what's the area of a rectangle? We know the area of a rectangle to be length width. So basically, we just need to simplify the expression base height plus length width. Now, the base, we'll let the base be this length along the top. Now, focus your attention on this triangle, the one on the left. I'm going to recognize that because theta is equal to that angle right there, we can say theta is also equal to that angle at the top part of that triangle. And using SOHCAHTOA, since 2 is equal to my hypotenuse, and since the base is this length along the top, I can actually say that cos theta, we know, is equal to adjacent over hypotenuse. Cos theta is going to equal b over 2. So that means b is going to equal 2 over cos theta. Or, sorry, b is going to equal 2 times cos theta, excuse me. So this length along the top, b, is actually just equal to 2 cos theta. Now, let's focus our attention on the height. We'll call it h. Again, focusing on that same triangle, the one on the right, and focusing on our angle in the top part that we've chosen to call theta, because that's what it's referred to in the diagram, we're going to say that sine theta is equal to opposite over hypotenuse, which is h over 2, or in other words, h is equal to 2 sine theta. Okay, so now this base times height that we have at the bottom of the screen, that's the same as 2 cos theta times 2 sine theta. Okay, now let's focus our attention on the rectangle that I've shaded in. The length of that rectangle is 3, as given in the diagram, and the width of it is the same as the height of the triangle, which we just said over here is 2 sine theta. So when you multiply everything out, what you get is 4 cos theta sine theta plus 6 sine theta. And that is an equation for the area of that trapezoid. So showing it again one more time, focusing our attention on this triangle. We could focus on the other one, they're the same. But what we can do here is we can say that the base is equal to 2 cos theta. And the reason being because cos theta is equal to b over 2. And then focusing on this other triangle, they're both the same, like we said. We can say that sine theta is equal to opposite over hypotenuse, so that's h over 2, so h is 2 sine theta. So we've already shown that, just to show it again, perhaps a little more neatly. What we can now do is say we have a formula. It's for the area of the trapezoid, it's 2 times 1/2 base times height plus length times width. So again, 2 times 1/2 is just 1, so it's base times height plus 3 times the height. So we establish that the base is 2 cos theta, the height is 2 sine theta, the height is 2 sine theta, and we get this expression right here. The area as a function of theta is 4 sine theta cos theta plus 6 sine theta. So writing that, focusing our attention on that, the area as a function of theta is 4 sine theta cos theta plus 6 sine theta. We can now determine our derivative. So what we're doing right now is establishing that second last algebraic line. The derivative is going to be the derivative of 4 sine theta, which is 4 cos theta. Derivative of the first times the second, which is cos theta, plus the first, which is just 4 sine theta, times derivative of the second. Well, if the second is cos theta, the derivative of the second is negative sine theta. And then we have 6 sine theta, so we're going to determine the derivative of that, which is 6 cos theta. And so putting all that together, we have that the derivative is just 4 cos squared theta minus 4 sine squared theta plus 6 cos theta. Okay, and that's what's written here. Now we're going to do something really clever here. If you look at this bottom expression, we've got cos squared theta, sine squared theta, and cos theta. Let's let sine squared theta equal 1 minus cos squared theta. You might recall one of our fundamental trig identities says sine squared theta plus cos squared theta equals 1. So by extension, we know that sine squared theta is equal to 1 minus cos squared theta. So what we're going to do is we're going to take that expression for sine squared theta, this 1 minus cos squared theta, and we're going to plug it in right there. Now, you might wonder, why are we going to do that? Well, first we do it, then we distribute the negative 4 in, and we get the second line shown here. We collect like terms. We get 8 cos squared theta plus 6 cos theta minus 4. We can actually factor out a 2 and then divide both left and right by 2. And we end up with 4 cos squared theta plus 3 cos theta minus 2 equals 0. The reason why we subbed in 1 minus cos squared theta for sine squared theta was so that we could get a quadratic in terms of cos theta. And when you have a quadratic in terms of cos theta, you can let it equal 0, and then you can use the quadratic formula if you can't directly factor. So what we have is a quadratic in terms of cos theta, where a is equal to 4, b is equal to 3, and c is equal to negative 2. And so cos theta will be negative b plus or minus b square root of b squared minus 4ac all over 2a. Plugging in the numbers, we get negative 1.1754 or 0.4254 for cos theta. Well, cos theta cannot be a number greater than 1 or a number less than negative 1. So that's an extraneous solution. Our only valid solution is 0.4254. If you look at the original diagram, you know theta has to be between 0 and 90 degrees. So what we do is we determine the cos inverse of 0.4254, and we determine that value only between 0 and 90 degrees, and we get 64.82. And so finally, what we can do is say that the area of the largest rectangle will be obtained by plugging 64.82 degrees in for theta in our area formula. And when we do that, we get 6.97, and we can say therefore that the largest possible area of the trapezoid is roughly 6.97 meters squared.